like, hopefully release a third kernel, and then sort of update how we do the rankings. So the rankings, in some sense, are probably not going to be stable here for the next couple of years. And that's one disadvantage we're going to have over LinPack, because it's not obvious in the beginning, and it was probably obvious to you guys, what the right measure should be. Right, so we're definitely not there. Okay, so this is data that Peter Kogi's been generating for a while. I'm sure Peter will have an update today, but I think the one simple thing that Graph500 was meant to show, this is almost brain dead in its insight, is that something like over 3+ orders of magnitude in change in scale in the first list, we had about 1 order of magnitude change in performance. Okay, so that says the smallest problem that was run, and problems down here, some of them are single node results in some sense, right? So if you look at some specialty implementations, my favorite, the other sort of is a Convey platform. This is a single node within FPGA, running all the way up through Blue Gene, which was the winner. Right? You only saw about an order of magnitude change in performance. And I think that, from the perspective of what we actually wanted to show in the benchmark, this demonstrates success. So the application people look at this and say, you're doing something easy. And I look at this and I say, look, the computer sort of fell over, right? If you look at this and update it to the November list that we had at supercomputing, we got a whopping 2 orders of magnitude change in performance, kind of at the high end versus the same, I guess it's 4 orders of magnitude now change in problem size. And what you'll see is actually the number 1 machine fits right in the middle in terms of problem size, so it's not actually solving the biggest problem. And it's really, what is that, less than 2 orders of magnitude off kind of the single node results. Okay, and that involves some pretty heroic programming on the part of a number of people to make that problem work. So these kind of graphs excite me. Several people have noted that there are no clouds in the Graph500 list. We specifically wrote the rules so that you didn't have to, so you could submit a cloud result if you wanted to. And I got a vendor who is friendly, who I'm not going to name in this audience, to give me some cloud results because several people have run them. And the answer is that as they scale the problem size from something relatively small to something, I don't know why it's not relatively big down here, but it's what the top machine runs, the performance tanks. Okay, so you can, there was a period of time where we were ranking more on problem size than on performance. The indirect result of that would have been that if you had a 486 on a tape drive, you could win the list. And so we changed that once we got enough results where people were throwing enough memory controllers at the problem to prevent that from happening. And I just find this fascinating, right? That in some sense, even though we didn't dictate this be the answer, you have to be a supercomputer even to win the Graph500 list or to place relatively well. Okay, so what does all of this mean? So essentially, we would contend that analytics problems are just fundamentally different from other problems, and I think you're going to see data to back that up when Peter talks. In terms of memory interconnect and new architectures, many of the things that we need are the same things that are necessary for high-end supercomputers. It's just that the assumptions about where the data comes from are going to be different. So in the end, when you get to kind of a system architecture for something that's doing analytics, right, data is likely to come in at you rather than be generated on the computer. I think I mentioned earlier that in some sense we're choosing an easy problem, so I want to kind of highlight that, right? So if you look at some typical sort of naively interesting algorithms for doing analytics, many of them are sort of between n log n and n cubed in memory or network or disk performance, depending on the algorithm. Where n is large, so that n log n itself may be in track. Okay, so you kind of usually tend to think I have an n log n algorithm, that's good enough. If n's big enough, it doesn't matter. Right? So if you're trying to kind of code this up, right, we jam these into simplifying paradigms in which they themselves may be limiting what we can do. So computers So we sort of solve the problems we know how to solve on computers and the other ones we don't worry about, right? And so my argument is that we really need to come to a consensus about what we need out of the algorithms in order to build computers that will solve those problems. And there's been a big initiative, at least in the United States, to start thinking about big data problems differently from the way we think about high-performance computing problems. And I think, in general, they sort of all fall into this particular model. So we'll just stick that. All right, so I alluded to some notions about what the system architecture for big data would look like. So ignoring Graph500 and kind of pulling into kind of how the applications are analyzed, the data is likely to start in disk and not in memory. Graph500 doesn't specify this, but that's kind of general. That no matter how big a computer you give it, the problem itself will never finish in memory. I see David Bader in the front, so David's probably more familiar with this piece of it than I am, in fact. And one of the things that we really want to be able to do is we want to therefore be able to kind of combine cloud-like and HPC-like components. So we tend not to talk about these two things together. In fact, they're different conferences, right? You run one in the fall on the cloud and one in the summer on HPC. And the problem that we're seeing is that what the cloud is actually providing is cheap, spinning rust on your network. And so people kind of try to jam their analytics into that model. It just doesn't work. And then there's another community, which is the HPC community, where you say, okay, well, my problem fits in memory. What you actually really want is some combination of both, right? And the problem is not so much technology as programming, right? You want to program that as a single massive computer. And so none of those particular problems are addressed by Graph500. Graph500 is strictly performance, but in general, I think if we think about the big data problem, this is the challenge, right? How do we mix components in a rational fashion such that we can do both kind of operations on the same platform? So what did we learn? Okay, it depends really on your perspective. Okay, so if you are trying to solve real problems, the Graph500 is laughably easy. Don't even show it to me. I don't even know what I'm looking at. If you love big, expensive supercomputers like I do, right? You feel great hubris if you're able to solve this problem with tremendous speed. If you're really into cloud computers, you're going to look at it and you're going to say, oh boy, that was a really expensive answer. I can't really solve that problem, but if I could, I would do a bigger one. And what I think we've really learned is that we have a relatively wimpy kernel, and the machines are not architected to solve it. Okay, and so if we can really kind of pick up on this message of the community, and if the problem is really important enough, what we really want is a re-architecture to do that, right? In the same way that data impact is important to a vendor, like important to a vendor. And there's sort of two dimensions to the computer performing poorly, right? One is in terms of efficiency. So how many memory controllers do I have to actually throw at the problem in order to get the number of edges that I traverse up? And the other is in terms of problem size, right? So we're not seeing a great increase in problem size tackled by Graph500 problems from list to list, right? So if I change the ranking metric to be based on problem size, what you would see is everybody would do about one scale up, right? In other words, they'd run one step larger problem and they'd take the performance penalty as a result. So what we're getting as submissions that are actually interesting because what they tend to be are the best performing problem size for a particular machine size, which is kind of interesting there. And then my contention is whoever rethinks this problem is going to have an opportunity to sort of dominate the future. So we didn't talk about the business areas of Graph500, but the ones that we've identified are cybersecurity, medical informatics, data enrichment, social networks, and symbolic networks. And I think if you think about some of those areas, so medical informatics, for example, is probably bigger in market size than all of high-performance computing. Right? I love high-performance computing. This is a community I grew up in. But I think these problems really, from an economic perspective, have the opportunity to be very, very disruptive. So in conclusion, I'm going to say once again, Lord Kelvin was right. If you cannot measure it, you cannot improve it. Right? And so what we're hoping to see is improvement by measuring. And what we actually have seen over the past 2 years is at least algorithmic improvement. Graph500 is an attempt to measure for what I would contend is a critical problem domain. We're optimistic that the 5 business areas that I named are actually big enough to justify future investment. And I think that there's going to be significant growth over the next decade, as well as impact on everyday life. So we'll have our BOP at 11:30. I hope to see many of you there. The list has actually finally grown to 88 entries. It's the Graph 88, which is pretty good. It started off as the Graph 9. So I'd say over 4 lists, that's pretty good. The winner's 7 times the ISC12.
15 times.
Which really surprised me. So.
15 times.
All right, thank you.
Thank you very much.
Я говорю, не наш.
So questions?
Yes.
So I had one question.